All right, welcome to The Explainer. Today, we are breaking down a concept that is absolutely essential in everything from physics to video game design, the unit vector. Now, it sounds a little technical, but it's actually a surprisingly simple idea with some seriously powerful uses.
So let's kick things off with a question that really gets to the heart of the matter. Imagine you're trying to describe a direction, maybe where a character in a game is supposed to be facing. But here's the thing, you don't care about their speed or how far they're going. How do you capture just the pure direction itself?
Here's what we're going to cover. We'll start with the what and the how. Then we'll get our hands dirty with some textbook examples, step it up with a few exam-style questions, and wrap it all up with the key takeaways. Let's dive right in.
Okay, first up, what is a unit vector? Let's get a really clear, simple definition for this.
So here it is, the big idea. You know that any vector has two things going for it, a direction it's pointing in and a length, which we call its magnitude. A unit vector is special because we've basically standardized its length to be exactly 1. That's it. By doing that, we strip away all the information about its length, leaving us with something that purely and only represents a direction. It's a way to put all vectors on a level playing field. Now, this is where things get really cool. Meet the superstars of the unit vector world, I, J, and K. These guys are the special unit vectors that point perfectly along the X, Y, and Z axes. You can think of them as the fundamental building blocks for every other vector out there. Seriously, any vector you can possibly imagine can be built just by mixing and matching different amounts of I, J, and K. They're kind of like the primary colors of the vector world.
Okay, so that's the what. Now for the how. How do we take any regular old vector and find its unit vector? Well, it turns out it's a super simple two-step process.
And it really is just these two steps every single time. First, you've got to figure out the vector's current length, its magnitude, using a bit of Pythagoras. Then, to shrink that vector down so its new length is exactly 1, you just divide the whole vector, every single component, by that length. It's like having an arrow that's 5 meters long. You just divide it by 5 to get a new arrow that's 1 meter long, but points in the exact same direction. Let's see it in action. Check out this first example. We've got the vector with components root 5 and 2. So step 1, apply Pythagoras. We take the square root of, well, root 5 squared plus 2 squared. That gives us the square root of 5 plus 4, which is just 3. So the magnitude is 3. Now for step 2, we just divide each component by 3, and bingo, there's our unit vector. This next one adds a little wrinkle. We need the unit vector for AC, but we're only given the vectors AB and BC. No big deal. First, we have to find the vector AC, which is just the sum of AB and BC. You just add them together. Once you've got that new vector AC, it's right back to our trusty two-step process. Find its magnitude, then divide the vector by it. Easy. All right, section 3. We've got the theory down, so let's roll up our sleeves and put it into practice with a few problems from exercise AA. This is where it all starts to really make sense. Okay, here's our first practice problem from the textbook. We need to find the vectors for AB and BC, and then figure out their resultant, AC. You know, this is the perfect time to hit pause and try this one for yourself. Go on, give it a shot. Okay, you ready? Let's break it down using the grid. To get from point A to point B, what do? We go 3 units to the right and 2 units up. So the vector AB is just 3, 2. Now for BC. From B, we go 2 units to the left, that's -2, and 3 units up. So BC is -2, 3. Now for the final piece, AC. And here's the solution. To find that resultant vector AC, we just add the components of AB and BC. So for the X component, it's 3 plus -2, which gives us 1. For the Y component, it's 2 plus 3, which is 5. And there's our final vector for AC, 1, 5. Let's try one more. This time, we're going to focus on vector subtraction. The goal here is to find the vector EF, and then show that it's the same thing as DF minus DE. Again, feel free to pause right here and work it out first. Okay, so if we look at the diagram, we can see that vector DE is 4, 1, and DF is -1, 4. Now, the key rule to remember here is that to find the vector that connects 2 points, like EF, you always subtract the starting points vector from the ending points vector. So we calculate DF minus DE. That gives us -1 minus 4 for the X part and 4 minus 1 for the Y part. Our final answer, -5, 3. All right, time to level up. We've got the fundamentals covered. Now let's see how this stuff shows up when it really counts in an exam.
This is where we apply everything we've learned, but under a bit of pressure.
Here we go, a classic exam question. This is a real bread and butter unit vector problem. You've seen this before and you know exactly what to do. Just stick to that two-step process. Find the magnitude, then divide the vector by it.
And the solution lays it out perfectly. Step 1, find the magnitude. Now, if you're sharp, you might just recognize this as a classic 3, 4, 5 triangle, so you know right away the magnitude of vector A is 5. Step 2, divide the original vector, 3, 4, by that magnitude of 5, and that gives us our final answer, our unit vector, 3/5, 4/5.
Okay, next question. And you gotta read this one carefully because there's a subtle but really important twist. We're not just finding the unit vector. We need the one in the opposite direction. They love to throw this in to see if you're paying attention. So the process starts out exactly the same. We find the magnitude of vector c. That's the square root of 5 squared plus negative 12 squared, which gets us 13. Then we find the normal unit vector, which is 5/13, negative 12/13. But here's the crucial final step. For the opposite direction, you just multiply the whole thing by -1. That flips it around completely, giving us our final answer, negative 5/13, 12/13.
All right, for our last exam question, it's a two-parter. Find the unit vector, and then, and this is super important, check that its magnitude is actually 1. This is a fantastic habit to get into for exams because it's a built-in way to confirm you did everything right.
And would you look at that? This is the whole point, isn't it? After we find the unit vector, we run the numbers to find its magnitude. We square the first part, square the second part, add them together, and take the square root. We get the square root of 1, which is just 1. It works perfectly. That's how you know for sure you've found a true unit vector. You've nailed it.
Okay, we've covered a ton of ground, all the way from the basic definition to exam-level problems. So let's just boil it all down to the absolute key points you need to remember.
So if you walk away with anything today, make it these 4 things. 1, the definition. Its magnitude is always, always 1. 2, its purpose. It's all about pure direction, nothing else. 3, the formula. It's that simple 2-step process. Find the magnitude, then divide the vector by it. And finally, number 4, remember that this process works for any vector, whether it's in 2D or 3D space. And that's our deep dive into unit vectors. So the final thought I want to leave you with is this. Now that you have this tool, this ability to isolate a vector's pure direction, where could that be a superpower? In physics, maybe for defining the direction of a force? In game design, for telling an enemy exactly where to look? Or in computer graphics, for figuring out how light should bounce off a surface? The applications are literally everywhere. Thanks for watching.